Hello everybody, this is Todd Frazee and this is ADVM 12, Unit 4, Dimensioning, Application and Limits of Size, which is a big part of dimensioning and tolerancing. Okay, in this unit you'll learn how to properly apply dimensions to technical drawings, making sure that they follow standard guidelines for clarity and accuracy. You will work with different geometric shapes, understand how fits and tolerances affect mechanical parts, and calculate size limits for features that need to fit together. We will also cover important industry standards like ASME Y14.5 2018 to help you create precise and functional designs. By the end of this lesson, you will see how dimensions and tolerances impact manufacturing and how to learn to include surface texture specifications in your drawings. Objectives. By the end of this lesson, you will be able to clearly apply dimensions in annotated models with a multi-view drawings by complying with stated general dimensioning guidelines. So there are guidelines for models and there are separate guidelines for drawings. They are similar, but not the same. Apply dimensions to any of the geometric shapes commonly found on mechanical parts. Cite the standardized types of fit for inch dimensions and describe general condition associated with each type. Calculate and apply limits of size for mating features. Moving on, you're also going to be able to explain rule number 1 and rule number 2 of the ASME Y14.5-2018 standard. Lucky for you, there's only 2 rules. Provide examples of the effects that dimensions and tolerances have on manufacturing. Complete a surface texture specification when provided the allowable variations. Okay, feature size. Regular feature size is a single size dimension, thickness, width, length, diameter, or spherical diameter. Irregular features of size are one enclosed shape or a collection of features that in combination establish a size boundary. Prisms and pyramids. Right rectangular parallelepiped or prism formed by 6 flat surfaces. Try saying that word 5 times fast. Only 3 dimensions are needed. A right square pyramid has 5 points that must be dimensioned. So these are examples of primitives. And the other primitive is a cylinder. So cylinders and models have to have a diameter symbol with in a length required, liter and dimension value on the same annotation plane, and annotation plane must be either cylindrical axis or lie perpendicular to that axis. Cylinders and orthographic views. The diameter with symbol and length is required, preferable to be dimensioned on non-circular view. That's something trend-wise, style-wise has changed. I was always taught to, in the past, to define cylindrical shapes in the view that it looks like a circle, but apparently it's preferred to do it as shown on the left here. And the diameter dimension usually is between non-circular and circular views, so you need to place the dimensions between the views as opposed to off the other side. And only one view if all features can be clearly dimensioned. So we got all our diameters on the common view if possible. Okay, flats on cylinders. A cut into a cylinder to provide a surface suitable for clamping something in a fixed location or set rotation angle. Dimension from the cylinder's far side or center line. Method determined by the surface's function. The far side for applications like clamping and center line for applications like mechanisms that go together. Cones. The right circular cone, the base diameter and height is required, or you can dimension it as the base diameter and cone angle. Do oblique cone, which is at a canted over, you have to have the base diameter, cone height, and apex offset. So in the example on the left, it's 250 thousandths offset. We're going to talk about holes next. So donut holes, things to consider, to ponder as we were talking about hole features on technical drawings. Donut holes are cut from the center of a donut. If it's a hole, does it have calories? If it does, would they be empty calories because it's a hole? And how can the glaze stick to the outside of a hole that only has interior features? Anyway, getting back to the lesson, hole size and models are dimensioned by giving a diameter, applied by a note, and a leader on one annotation plane, coincident with penetrated surface, as shown on the left. May be increased to apply dimensions to hidden features, and section views to minimize this can be used, and the leader line is solid. Those are on models. On orthographic views or drawings, dimension by giving a diameter may specify hole diameters in non-circular views when shown in section view. Large holes dimensioned by placing dimension line and size value inside the hole. The dimension line must pass through the center of the hole. Small holes dimensioned with the leader connected to size value, and leaders point towards the center but terminate at the edge of the hole. Now the standard here, they talk about large holes placing the dimension inside the circle. I believe that's style, as we'll see in one of the images. The author prefers it, but he actually notes that ASME Y14 doesn't require that, doesn't even mention it. Okay, so hole location, dimension to the hole center. Extension lines apply to the hole center and extended past the dimension lines. Center lines drawn between holes when a single dimension locates multiple holes aligned with each other. And locating dimensions on one view side of the view and hole specifications on the other side of the view. And removed view of a hole pattern can reduce cross dimensions. So that's where it's very similar to a detail view. It's shown removed. It's labeled like with a letter like a detail view, but you don't have a circle circling the primary view, that its parent view where it came from. And they often have a scale factor associated with them. Okay, hole depth. It's assumed to go through the part in an orthographic view unless the depth is specified. You're going to use the word through that follows a diameter if it's not clear. And it's unnecessary for models because you can see from the model whether the holes go through or not. The depth symbol is preceded by a specific depth. So that's the down arrow. And then you specify the depth for blind holes and specify the total depth where a hole passes through multiple walls. Okay, so in the example on the left, the reason we have to say through on the one through hole is there's two other holes, the same exact diameter, that have a depth to them. So to differentiate the one location that goes all the way through, you clarify it with the letters through. Now I know SolidWorks defaults to putting through all, so I guess technically to meet the standard you should delete the word all from the notation. And again, it's not necessary if all the holes go through and you can't confuse it with a different hole. It's implied that it goes through. so you don't need to add the notation. It's optional. Okay, hole depth requirements. The depth specified followed by a diameter. The depth is the distance to the full diameter extends to, okay, not the tip. And specify the shape is required at the bottom of the hole. And drill points are drawn in the orthographic views as 120 degrees unless a specific angle point is specified. So the standard drill tip for decades was 118 degrees, but the drawing convention was to just draw them at 120 because it's close enough for a graphic. Again, you don't scale off that. You're just trying to demonstrate that it's allowable to have a drill point there. Okay, the hole depth. If the hole depth is greater than 3 to 5 times the diameter, it may require special tools to process, or multiple drill bits, boring bars, or gun drills for really long holes. Counter bore. So step to increase to an existing hole diameter. The bottom is perpendicular to an axis, specified by providing hole diameter, hole depth, when required, the counterbore diameter and depth and fillet radius. Remaining material may be dimensioned for depth. Commonly used to recess fastener heads on screws. Countersink. Angular increase in hole size, specified by providing hole diameter, countersink diameter, and countersink angle. Commonly used to recess fastener heads on flat head screws and break sharp corner edges of holes. Cornersink values. The angle is equal to the angle of the screw head if used to recess the fastener head. Countersink diameter is equal to the sharp diameter of the screw head. And diameter on the irregular surface is equal to twice the minor radius of the countersink. So if it's on an irregular surface, you need to go to where it's deep enough that the head would fit below a cord struck across the arc of that irregular surface. Counter drill. It's similar to a countersink, but you go deeper. It's a cross between a counterbore and a countersink, specified by providing hole diameter, counter drill diameter, and counter drill depth. Counter drill angle, specified when remaining material or clearance are important, and the angle may be applied as a dimension or included in the notation. It's acceptable to use the abbreviation C drill when it's used in a note. Spot face. Similar to a counterbore, but does not go as far into the part, doesn't remove as much material. Its purpose is different. Instead of recessing the head, it's to give a flat spot for a washer to sit. The minimum information is the hole diameter and the spot face diameter. No specified depth requires adequate depth to create a flat of a specified diameter. So if it doesn't have a depth call out, you just go as deep as you can to barely make a flat surface that's the diameter specified on the drawing. A specified depth controls depth without regard to the flat produced. So if you tell a specific depth and the flat's not big enough, then it's not going to perform the way you want. And a fillet corner radius is specified when it's required. Angles. For models, never imply the angle. It must be measured or queried in the system if dimensions are not shown. Perpendicular surfaces in orthographic views are implied to be 90-degree angle without any dimensions shown, and dimensioned by showing degrees between features that create it, or dimensioning endpoints or vertices. Angle values and application. Angle specification notation can take several forms. You can have degrees. You can have minutes. There are 60 minutes in a degree, just like there are 60 minutes in an hour. There are also seconds. If it goes even to another level of accuracy, there are 60 seconds in every minute. And there's decimal, which breaks it down into hundredths. So 30 degrees in 15 minutes is the same as 30 degrees and 0.25 degrees. They're both measures and notation for 30 and a quarter degrees. Center of a dimension line arc at the vertex of an angle, and extension lines are required to intersect at a vertex of an angle. Chamfer. It's a small inclined surface used to eliminate abrupt or sharp edges on a part, to facilitate assembly of close fitting parts. Diameter included angle for holes. Angle and length of one side for edges of cylindrical features. Length of the chamfer side, or the length of one side, and the angle for edges of non-cylindrical features. It's also permissible to put a note to specify that chamfers are at 45 degrees if they are common, but it can cause ambiguity if you have multiple chamfer angles, and so it's not recommended to use a general note unless it applies to the entire part. Taper is a ratio of change in diameter per unit of length. It's used to locate parts relative to one another or hold parts together. This dimensioning method depends on the amount of control desired. Okay, so your options are of taper types. There's standard machine taper, intended to mate with an existing machines and tools. The dimension is noted by the taper name and number, but you have to reference a standard for those sizes. Non-standard taper diameter is fitted to a gauge. Specify gauge line in location and diameter, and taper on the diameter per unit of length, not defined in the current standard of ASME 14.5. Non-critical tapers are dimensioned by giving an included angle, length of taper, and a diameter at one end. Arcs and models. Dimensioned with the leader placed outside of the part, with the geometry and terminated with a dot on the feature surface, of the radius. A radius dimension leader terminates on an edge or arc surface, so it has an arrow if it's on an edge. And the leader is oriented to pass through the arc center, or at least pointed at it, and extend past the center if outside the part geometry, and always outside the object. Arcs and orthographic views. The arc center is represented by two short cross lines. The leader line for the radius dimension is oriented to pass through the arc center. Leader extends from the arc center to arc if space permits, and the radius value is shown outside the part or in a break in the leader. So you can have the number in a break in a leader, like the 750 thousandths call out shown on the left. Okay, arc location. Dimensions applied to arc center or surfaces that define arc tangents. The method affects the tolerance zone shape if a plus and minus tolerances are applied to radius dimensions. Arc center creates two concentric boundaries that float within a tolerance. Arc tangents can create a crescent shape located adjacent to surfaces if dimensioned that way. So if you give them the tolerance to adjust the arc endpoints, and that's different than the profile, you can get an effect of gouging in those areas. So concentric boundaries are better from the radius dimension. It's wrong to show dimensions for both arc center and tangents because it'd be over constraining or over defining the feature.